For the first question, we're asked to name the following compounds. For the first compound, we have a cyclohexane ring, where we have carbon number 1, 2, 3, 4, 5, 6 in the ring. This is going to be 1 bromo, so 1 bromo because we have our bromine group here, and 3 methyl, we have a methyl group right here, cyclohexane, but we have 2 stereocenters. So first, before we write down the name of this, let's assess what these 2 stereocenters are. With the stereocenters, we usually number the substituent priority. So attached to this carbon here, which is our first stereocenter, we have bromine here, and we have carbon here, and we have carbon here, and we have hydrogen, which would be on A dash. This is convenient because the 4th ranked substituent is already in the back. Our first ranked substituent is bromine. Carbon, this carbon right here and that carbon right there are both CH2, so these are tied. So we need to go one further. So looking at this carbon right here, we've got 2 additional carbons connected. Looking at this carbon right here, we have 1 additional carbon connected. So that means this carbon here wins in priority. So that means this is 2 and that is 3. So that carbon, there's 3. So looking at the rotation that this is going, 4 is already in the back. That makes it convenient. Carbon number 1, 2, and 3. So that is the counterclockwise direction. And if you are looking at it, if it goes in the counterclockwise direction, that is an S stereocenter. So we have an S stereocenter there. I'm going to erase some of this stuff so it's not too confusing when we look at the next one. Alright, so here for carbon number 3, we have our methyl group attached. We have a carbon there, and we have a hydrogen that is coming out at us on a wedge. That carbon's definitely ranked 4th. The methyl group is ranked 3rd, so that's behind these 2 CH2s because they have carbons attached to them. This carbon attached to the bromine is definitely going to rank highest because this CH2 only has a methyl group attached to that, so that's number 2. So in this case, one way to do it is flip your substituents. I think it's easier actually if you just essentially assess the stereocenter and know that you're incorrect with your assessment. So here, if we say we've got start at carbon number 1, then 2, then 3, that's rotating in the clockwise direction. So that would be an R stereocenter, but 4 is sticking out at us. So really, it's like we would be looking at it from the other way, and if that was the case, it would have the opposite rotation. So this is actually also an S stereocenter. So this is an S stereocenter, not an R stereocenter, even though it's rotating that way. 4 isn't in the back like the rule says, so we were incorrect with our first assessment. We are correct when we flip that, so it's an S stereocenter. Alright, so this compound is 1 S 3S 1 bromo 3 methyl cyclohexane. Alright, for the next compound, here we've got 1, 2, 3, 4, 5 carbons in our chain. Our alkene starts here, which it looks like based on that, I should probably number it the other way because that's the only relative group on here. So the first carbon is going to have priority. So we've got carbon number 1, 2, 3, 4, 5. Now this alkene is a transalkene. This ethyl group is going up and that methyl group is going down relative to this. We have a hydrogen there and a hydrogen there. The way I like to look at that for cis and trans, if your most prominent substituents are both on the top or both on the bottom, it is cis. If they're the opposite, so one's on the top, like this ethyl group is on top, and this methyl group is on the bottom. Those are our most prominent functional groups. They would essentially rank highest when we're looking at RS stereocenters. Then it's a transalkene. So in this case we have a transalkene, but for naming we usually stick to E and Z for naming. So going back here again, numbering these, we've got 1, 2, 3, 4, 5. This is an E alkene. Our most prominent groups coming off of our sp2 hybridized carbons are not on the same side of the alkene, so this is E. So this is 2E pentene. And then the 2 you don't have to put since we only have one alkene here, so that 2 is not necessary. So often you're not going to see that. Also, if you have only one stereocenter, you don't need to number that because there's only one stereocenter there. Alright, looking at the next compounds here, we've got carbon number 1, 2, 3, 4, 5, 6. So we've got hexane. We have a methyl group at carbon number 2 and carbon number 4. For the methyl group at carbon number 2, this is not a stereocenter. First of all, it's not specified, so we couldn't say what it was even if this was on a dash or a wedge. But we've got 2 methyl groups attached to carbon number 2, which is why it's not a stereocenter. We don't have 4 different things attached. Alright, carbon number 4 is a stereocenter. On this carbon, we've got the rest of the carbon chain over here, and we've got a methyl group here and an ethyl group here. Looking at priority, this is convenient. We have a hydrogen there. That's ranked 4th. That's already in the back. This methyl is going to be 3rd. The ethyl is 2nd, and the rest of the chain is 1. So just for clarity's sake, let me erase some of this other stuff here. So that's not a stereocenter. Our more substituted alkane is going to be our first ranked, and all I have left is the numbers for the rankings. So looking at what we're going to assign this, 4 is already in the back. Oh, let me erase this number 4 too. So 4 is the hydrogen that's already in the back. Here we're going in the counterclockwise direction, going from 1 to 2 to 3. So this is an S stereocenter. So this is S and 2, 4 dimethyl hexane. Alright, on the previous one I emphasized that here we don't, if this could be drawn as a wedge here, that'd be a little bit misleading because this isn't a stereocenter. That's basically what happened here. So on this carbon right here we have 2 ethyl groups attached to it. Some of you did label this as a stereocenter, but that is not a stereocenter because we have 4 different things attached. Looking at our substituents, I'm going to start on this side because that's my first substituent off carbon number 3. So this is carbon number 1, 2, 3, 4, 5, 6, and 7. So we've got heptane, and we have bromine at the 4 position. We need to assess what this stereocenter is. So I'm going to erase these now that we're on the same page with that. So with bromine, that is in the back, hydrogen is in the front. Bromine's ranked 1st, hydrogen's ranked 4th, and then we've got CH2 here. So it's got 2 hydrogens. This carbon here has a hydrogen attached, but we have 2 carbons attached to this carbon here. So this is going to be ranked 2nd, and this is going to be ranked 3rd. So looking at the rotation of this, 4 is coming out at me, so I'm going to do the rotation, but I know that I'm wrong because 4 needs to be in the back for you to have a correct assessment of that rotation. So going from 1, 2 to 3, that is a clockwise rotation. However, I'm incorrect, so even though I've assessed that to be R because that's a clockwise rotation, 4 is not in the back, so I'm incorrect on that. So this is an S stereocenter. So definitely S. So we decided we had heptane, we have an ethyl at the 2 position, bromine at the, an ethyl at the 3 position, and bromine at the 4 position. So this is going to be S, and bromine alphabetically is before, so S3, oops, bromine's at carbon number 4, ethyl's at carbon number 3, so S4 bromo, 3 ethyl, heptane. All right, for this next one here, I'm going to start here. So this methyl group is the first substituent from any place that I could start to make the longest chain. So that is carbon number 1, that's carbon number 2, that's 3, 4, 5, 6, and 7. So we have heptane again. We've got a methyl at the 2 position, a methyl at the 3 position, and an ethyl at the 3 position. So we've got methyl and ethyl as our 3 substituents there. And I'm going to go ahead and assess the stereocenter for this. So I'm going to erase all this stuff to figure out what the stereocenter is. So this carbon right here is our stereocenter. That's the only carbon where we have 4 different things attached to it. Methyl is the lowest ranking, so CH3 is the lowest ranking. This carbon right here has 2 carbons attached to it, so that's going to be the highest ranking. And then we've got a CH2, which ties with CH2, CH2, which beats CH3. So this is going to be second, and that's going to be third. So now that I've got all my rankings, 1, 2, 3, 4. If you look at this carbon essentially from this direction, 4 is going in the back there. So my isopropyl group is essentially behind the page, and my long carbon chain here, my 1, 2, 3, 4, my butane chain is coming out from the page. So I can actually assess the stereocenter looking at 4 in the back from this angle for the arrow that I've drawn. So looking at this, this is 1, 2, 3. So that is going clockwise. So that would be an R stereocenter. R, 3 ethyl, and carbon number 2 and 3, 2, 3 dimethyl heptane. Alright, for the next we're going to draw 2 chair structure representations of the following compound and figure out which is the most stable representation. So I'm going to go ahead and draw my chair. I got a little bit crazy on that second line there. Okay, there, and then reconnect there. And erase that. So I'm going to say this is carbon number 1, that's 2, and that's 3. So this could be carbon number 1 right there, and 2, and that means that's carbon number 3. If I was actually numbering this, it would be the opposite of that. So this would be carbon number, so that would actually be 1, and that'd be 2, and that'd be 3. So let me just go ahead and switch that orientation anyway. So that's carbon number 1, 2, 3. So I'm going to switch this orientation as well. So we'll say this is carbon number 1, and that's carbon number 3. My ethyl group is in the up position. In this case, at the high point on the chair, the up position is the axial position. So I've got an ethyl group there. On carbon number 3, I have a methyl group. So that's carbon number 3. That's also in the out position on this representation. So this is out. So I need to make it up there. And up happens to be the axial position. So that's one representation. I'm going to go ahead and flip this chair now. So flip that down there and flip that up there. which means that now I have my ring looking something like that. And now my methyl group is still in the up position, but that carbon right there is there, so I've got a hydrogen in the down position, and I need to make that line parallel to that bond right there, so that goes there. So that's my ethyl group, and both are still in the up position, but now they're both equatorial, so this is going to be by far the more stable compound. Alright, for the next, draw the enantiomer of the following compounds. So an enantiomer means that if there are any stereocenters, all of them are flipped to be the opposite of what they are. So I'm going to just redraw this structure here. And my bromine was on a wedge. I'm going to put it on a dash. And my methyl group is on a dash. I'm going to put that on a wedge. For the next compounds, my ethyl group was on a wedge. I'm going to make it on a dash, so that now has the opposite stereocenter. For the next compound, bromine was on a dash. I'm going to put it on a wedge. Like we talked about before, that diethyl group that's actually, that carbon right there is not actually a stereocenter, so it doesn't really matter how I draw that. I basically do the same compound before. And for the next one, basically when you draw this, two things have to be flipped. So I'm going to flip my butyl group to become what's on the dash. So there's one carbon, two carbons, three carbons, four carbons. So 1, 2, 3, 4, that's my butyl group. And my isopropyl group is now on the wedge. And my methyl group is still there. So this is represented a little bit awkwardly from the start. But still, when you flip the stereocenter, you just flip two substituents. So that is the enantiomer. So if you wanted to double check yourself, you could essentially assign that stereocenter, that one, and these two. And hopefully when you reassign these stereocenters, those are all flipped to be the opposite, because that essentially fits the definition of an enantiomer, where you have all opposite stereocenters. For the next, draw a diastereomer of the compound. So for this, when you're looking at diastereomers, not all stereocenters are flipped. So I'm going to draw my cyclohexane ring. I'll keep bromine the same for the first one, and flip the methyl group orientation. So that's one diastereomer. And then for the other one, I will leave the methyl group the same and flip the bromine. So that is the other diastereomer. So those two are diastereomers, and then an enantiomer would be flipping both, so we've already drawn that enantiomer up there. Alright, this one does not have a diastereomer, so this only has one stereocenter right there. If I flip that, then that gives me the enantiomer. So it has an enantiomer, but it does not have a diastereomer. So again, it only has one stereocenter. If you change the orientation of that, then that means you get the enantiomer. So there's no option to make a diastereomer. Alright, draw the Newman projection of this looking down the C2-C3 bond. So for when we were numbering this, we said 1, 2, 3, 4, 5, 6, 7. So the C2-C3 bond is right here. Now when numbering this, it would actually be a little bit easier to just say that this is 1, 2, 3, so we're in the same plane. So another representation of the C2-C3 bond is right there. That'll be easier to draw looking down that C2-C3 bond, just because those are all in the plane that we're looking at. So for this Newman projection, the front carbon, I'm actually going to go ahead and draw the hydrogens in there too, just for reference. So the front carbon is the dot on the Newman projection. So in this case, the front carbon is there, and I've got my methyl group coming out here, my hydrogen coming there, and this hydrogen there. So it's not a stereocenter, so it really doesn't matter the way that you draw the substituents off of it. And then for the back carbon, that's a circle. So that is that carbon. On that back carbon, I've got my long carbon chain coming off here. So that's that, and that's got the bromine attached to it, and then the propyl group attached to it. And then I have a hydrogen as well as an ethyl group as well. So the ethyl group is more in the up position, and my hydrogen's right there. Again, since these aren't stereocenters, it doesn't really matter the exact orientation you draw them. And this probably wasn't the best choice, picking the C2-C3 bond. Usually you'd be asked for something like the C3-C4 bond, so that stereocenters can be specified more efficiently. For the next question, draw the bond line structure of the following Newman projections. So this carbon right here is the carbon that I'm looking down, but this carbon is not the start of the chain. So really, if we think about the carbon chain, it's going to be that one right there. So I'm going to go ahead and draw the ethyl group. Now that is attached to this carbon right here, which is that carbon right there. So that carbon right there is attached to an ethyl group, which is good. That's what I have now. It's also attached to a methyl group and a hydrogen. So I'm going to go ahead and draw in the methyl group and the hydrogen, and just simply not specify those stereocenters. So drawing in the methyl group and the hydrogen, I'm going to say I've got my methyl there and my hydrogen there, and I've got the rest of the carbon chain. So now this carbon right here is this carbon right here. So this carbon that I'm pointing to on my bond line structure is that circle. So what that carbon has attached to it is an OH, a methyl, and an isopropyl group. So that is the isopropyl group. So that is this compound. Now I can specify the stereocenters on these as well. So looking at the stereocenters for this carbon right here, I'm going to look at it this way. So that way hydrogen's in the back. So this would be ranked 1, 2, and 3. So thinking about kind of turning this a little bit in 3 dimensions, and starting at 1 and going to 2 and 3, that is an S stereocenter. So this should be an S stereocenter. And then looking at the back carbon, we've got our OH here, so that's going to be ranked 1. This front carbon is connected to that. That's got a methyl and an ethyl, which beats the methyl and methyl. So that's going to be 2, and this is going to be 3, and that methyl is going to be 4. So I'm actually going to look at the back carbon from this same direction. Where now I've got my oxygen is ranked first, this carbon that's coming towards you is second, and that carbon back there, the isopropyl group, is third. So that is also an S stereocenter. So now that I've defined the stereocenters, I can make these what they need to be. So basically double checking, I'll just try one and see if it's right, and if it's not, then I'll flip it. So this carbon here is ranked first, that one's second, that one's third. So 1, 2, 3, that's actually an R stereocenter. So I'm going to flip this to make my methyl on a dash and my hydrogen on a wedge. So just checking one more time to see if that's an S stereocenter. Now I've got carbon 1, 2, 3, all the same ranking, but when I do this, I know that the stereocenter is opposite, so that rotates R, it's an opposite stereocenter, so it's S. For ranking this stereocenter here, similar to what we discussed above, so the oxygen is going to be ranked first. My carbon with both a methyl and an ethyl is going to be ranked second, and the isopropyl group is going to be ranked third. So we also have hydrogen there. It's got 2 methyls versus a methyl and an ethyl, so essentially the ethyl here beats the methyl here. So looking at the rotation of this, we've got 1, 2, 3 with 4 in the back. So that would actually be an R stereocenter, so I need to flip those again, so I'll just redraw the compound here. This I'm going to actually approach it in a different way. So this OH is straight up, and this carbon right here is the front carbon. So that is my OH, that's straight up, and that's the front carbon. This goes then to the next carbon, so that circle carbon is this carbon, and this is attached to an ethyl group, which if I rotate it in the way that I'm showing now, my ethyl group is in the back and my hydrogen is facing towards you. On the back carbon, we have a methyl group facing straight down, and we have an isopropyl group in the back, and we have a methyl group in the front. So there's my methyl group in the front. Now hopefully we can double check this and make sure that makes sense. So here I've got my methyl group in the front and my hydrogen in the front. So on this carbon here we've got the hydrogen in the front and the methyl group in the front. So that checks out. It makes sense those should be on the same side. And then in the back we have the ethyl group and the isopropyl group. So my ethyl group is on a dash there and my isopropyl group is on a dash there. So that checks out for the orientation. Now this isn't the best representation of it, but this actually matches a little bit closer to that exact Newman projection. We can also still go ahead and double check our stereocenters. Actually, there's really no reason in this case, since we didn't reorient anything, there's no reason to double check the stereocenters on these. So I think in this case we can just leave it as it is. If you wanted to check the stereocenter up here and match it with that, you could double check your work, but what I've drawn is the bond line structure of that Newman projection.